In this video, we'll learn about measures of relative standing, which are numbers showing the location of data values relative to the other values within the same dataset: z-score, percentiles, quartiles. And we will also learn how to build and interpret the box plot. A z-score is also called standard score or standardized value, is the number of standard deviations that a given value x is above or below the mean. The z-score is calculated by using one of the following formulas. Z-score for the sample is x, the value in the sample, minus sample mean divided by sample standard deviation. Population z-score is equal to x, the data value, minus population mean divided by population standard deviation. Z-score is rounded to 2 decimal places. Before we proceed with the example, let's look at some important properties of z-scores. A z-score is a number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as the numbers with no units of measurements. A data value is significantly low if its z-score is less than or equal to -2, or the value is significantly high if its z-score is greater than or equal to +2. If an individual data value is less than the mean, its corresponding z-score is a negative number. We'll now look at how to calculate the z-score and what is the use of the z-score in real life. Let's read the example. Which of the following 2 data values is more extreme relative to the data set from which it came? The 4,000-gram weight of a newborn baby among 400 weights with sample mean 3,152 grams and the sample standard deviation 693.4 grams, or the 99 degrees Fahrenheit temperature for an adult among 106 adults with sample mean 98.2 degrees Fahrenheit and sample standard deviation 0.62 degrees Fahrenheit. The formula to calculate the z-score of a data value is the data value minus the sample mean divided by the sample standard deviation. We'll start with the first example. Our x is 4,000 gram minus the mean of this data set is 3,152 divided by 693.4 is equal to 1.22 rounded to 2 decimals. Remember, z-score is rounded to 2 decimals. And the second z-score. In the second example, our x value is 99 degrees Fahrenheit minus the mean 98.2 divided by standard deviation 0.62 is equal to 1.29 rounded to 2 decimals. Out of these 2 z-scores, the more extreme is the z-score that lies farther from the mean of that particular data set. 122 is closer to the mean than 129. Therefore, the data value with the z-score of 1.29 is a little bit more extreme than the data value with the z-score of 1.22. Z-scores can be used to identify significant high and significant low values. The data value with the z-score less or equal -2 will be considered significant low value. The data value with the z-score of 2.0 and up will be considered significant high value. Let's read the following example. The lowest platelet count in the data set is 75. Is the value significantly low? Assume that the platelet counts have a mean of 239.4 cells per microliters and the standard deviation of 64.2. The platelet count of 75 is converted to a z-score by subtracting 239.4, the mean, and divided by 64.2, standard deviation of a sample. The z-score is equal -2.56. -2.56 is significantly less than -2. Therefore, the value of 75 will be considered significant low value. Let's now look at another measure of relative standing, percentiles. Percentiles are a measure of location denoted by P1, P2, P99, which divide a set of data into 100 groups, with about 1% of the values in each group. If that was our data set that starts at a minimum value, ends at a maximum value, the whole data set is considered 100%. If we divide the whole set into 100, then each mark will indicate a percentile. Data value that is located in P1 will be considered the data value that separates the low 1% of the data from the highest 99%. Right here in the middle will be percentile 50, the data value that will separate the low 50% of the data values from the high 50% of the data values. If we divide the whole set into quarters, then quarter 1 will indicate 25th percentile. Data value with the 25th percentile is the value that separates the low 25% from the high 75%. Quartiles divide the data set into 4 quarters. Quarter 1, P25 or 25th percentile. Quarter 2 or 50th percentile. It is also median of a data set. Quarter 3, 75th percentile. And quarter 4. To find the percentile of a data value, divide the number of values that are less than the data value you're looking for by the total number of values in the data set and multiply by 100. Let's review the following example. The Airport Verizon cell phone data speeds listed below in a table and are arranged in increasing order. Find the percentile for data speed of 11.8 megabytes per second. 11.8 data value is located on the 21st place. We can count the data values 10, 20, 21. The total values are 50. So to find the percentile of data value of 11.8, we divide the number of the values that are less than 11.8, which is 20, by the total number of values, 50, times 100 equals 40. A data speed of 11.8 megabytes per second is in the 40th percentile. We can interpret it as data speed of 11.8 megabytes per second separates the lowest 40% of the values from the highest 60% of values. Now we'll look at the process of converting a percentile to a data value. We'll start by sorting the data from least to greatest. Then we'll compute the location of the data value using the following formula. K, percentile that we're looking for, divided by 100 times n, the total number of values. If the location is a whole number, then the value of the kth percentile will be midway between the nth value and the next value in the sorted set of data. We find the percentile by adding the nth value and the next value and dividing the total by 2. If the location is not a whole number, then we round it to the next larger whole number. The value of the percentile is the nth value counting from the lowest. It sounds as a complicated process, so we will look at the example. Refer to the sorted data speeds below. Find the 40th percentile, denoted by P40. The data are already arranged in order, so we will use the formula to find a location of the data that indicates the 40th percentile. L is equal K, the percentile, in this case 40, divided by 100 times the total number of the data, which is 50 in this case. L is equal to 20. The location of our data is 20, which will be 11.6. If the location is a whole number, then we go to the next place and find the midpoint between the data that is located in the 20th place and the next data. 11.6 plus 11.8 divided by 2 is equal to 11.7. 40th percentile is 11.7 megabytes per second. That means that 11.7 is the data value that separates the low 40% of the data from the high 60% of the data. Let's say we want to find 75th percentile. We start with using the formula to find the location of the data value, k divided by 100 times n. K in this case is 75 divided by 100 times the total number of values are still 50 equals 37.5. The location is a decimal, therefore we round it up to the next whole number, 38. The data value that separates the 75 low percent from 25 high percent of the data, located in the 38th place. 10, 20, 30, 21.5 data value is located on the 38th place. So P75 or 75th percentile is data value 21.5 megabytes per second. Now that we understand the meaning of percentiles and know how to find certain percentile, and we understand the relation between percentiles and quartiles, and know that percentile 25th indicates quarter 1, percentile 50 indicates quarter 2 or median of a data set, P75 indicates third quartile, we can learn how to build box plots. In order to build box plot, we'll need what it's called a 5-number summary, which consists of the minimum value, quarter 1, quarter 2, quarter 3, and the maximum value in the dataset. We'll use the same example of Horizon data speeds to build a box plot. The minimum value is 0.8, maximum value is 77.8. Using the formula to locate the data of the 25th percentile, 25 divided by 100 times 50 equals 12.5. Remember, this is the place, this is not the data value. If the location is a decimal, we round it off to the next whole number. We're looking for the data value that is located on the 13th place. 10, 11, 12, 13, 7.9 is quarter 1. Now let's find quarter 2 and quarter 3 using the same techniques. The data for the 50th percentile, or quarter 2, is located on the 25th place. 25 is a whole number. 13.7 is located on the 25th place. So we go to the next value, 14.1, and find the midpoint between 13.7 and 14.1. Quarter 2 is 13.9, and quarter 3 is the data value that is located on the 38th place. Because the location is a decimal, so we round it up to the next whole number. The data value that is located on the 38th place is 21.5. Now let's build a box plot using the 5-number summary. The box plot is also called box and whiskers diagram because it consists of the box and the whiskers. The minimum value is on the left. The maximum value is on the very right. This is quarter 1. Quarter 2 is the middle, and quarter 3 is 21.5. To find the outliers of the dataset, we use what it's called interquartile range. Interquartile range measures the variability of data about the median. It's the distance between the first and the third quartile. A data value is considered an outlier if it's substantially above quarter 3 or significantly low than quarter 1. To be more precise, it's 1.5 of the IQR above quarter 3 and 1.5 of the IQR below quarter 1. Let's determine the lower and upper cutoff scores for the outliers in this dataset. To find the outliers, we find 1.5 of the IQR and add it to quarter 3, 21.5. Interquartile range of this dataset is 21.5 minus 7.9, 13.6 equals 41.9. That is the cutoff score for the outliers that are significantly higher than the rest of the data. So if you look at the data set, we have 43, 55.6, 71.3, and 77.8 data values that are higher than the cutoff score of 41.9. I'm going to modify my box plot just slightly because we have a little bit more outliers. I'm going to extend the tail with the maximum value. This is the cutoff score. Here will be the outliers: 43, 55.6, 71.3, and finally the maximum score, 77.8. To find the cutoff score for the data value that will separate significant low values from non-significant values, we multiply IQR times 1.5 and subtract from quarter 1, negative 12.5. Of course, the speed cannot be a negative number, so there are no significant low outliers, but there are quite a few of significant high outliers. We'll now learn how to build the box plot using StatCrunch software. I entered the values of Verizon speeds and saved the data in my data sets. Now I want to build a box plot, which is type of the graphs. So select graph, box plot, select the column, var 1, click option draw boxes horizontally. You can choose the markers mean and median. Let's do that. So we verify that the median is our quartile 2. Click compute. Here's our box plot. We can point in any place in the box plot to see the 5-number summary. Quarter 1, 7.9. Quarter 2, or our median, 13.9. Quarter 3, 21.5. The lower limit, 0.8. The upper limit, 38.5. The mean of this data set is 17.6 approximately, which is slightly different than the median of 13.9. The outliers are marked as dots. And if we point at the dot, we can see the value of the outlier: 43, 55.6, 71.3, and maximum value, 77.8. More topics coming up. Stay tuned. Subscribe for the updates. I will see you soon.